So if you were with us last week, we made use of a stroboscope to stop motion that was happening very quickly. And today I'd like to talk a little bit about a wave. I have a string here with a small mass connected to the end of it to provide a little tension. And this string likes to vibrate. And I have the string actually is going to be pushed up and down by a small motor over here with a little screw that's offset from the center so that I can create a wave on the string. And it just so happens, as you'll be able to see hopefully in a moment, that there are points in the wave that don't appear to move. And that represents actually 1/2 of the wavelength of the wave. And if I catch the frequency, in physics we know that the velocity of a wave is equal to its frequency times its wavelength. So we're actually able to measure that, and we can compare it. There's a formula that tells you if you know the tension and the property of the spring that you're using, you can also figure the velocity. And normally those come out very close to each other. So we're going to try this little experiment here. We'll turn down the lights so that it's possible for you to see both the motion of the string, but also the effect the strobe has when we shine it on it. Okay, so we've dimmed the lights. I'm going to start the electric motor here. And the electric motor, if I adjust it just a bit, creates a wave on the string. There's a point here and a point here where it appears the string doesn't move at all. That's 1/2 of a wavelength. From what we call one node to another, if you do 2 of them, that's 1 wavelength. Now, it appears that that spring is moving quickly, and it is, but with the stroboscope, I'm capable of stopping the motion on that string. So what I do is turn the strobe. Right now the strobe's actually going on and off roughly twice as fast as that string is going up and down. I want to get it to where it's just, there we go, almost. See if I can adjust it a little better. I have that string almost motionless. So if I know how fast my strobe is going on and off, I know the frequency of this wave. And since I can easily measure the wavelength of the wave, you can see the string looks like it's not moving all along its entire length, but in fact, the motor's going up and down very quickly, and it's creating the wave on the string. So we're able to calculate the velocity of the wave because we know its wavelength and its frequency. So waves don't only just happen on strings. Of course, everyone's familiar with water waves, but we also know all about sound waves. And I have here a wooden organ pipe. It's actually got keys marked on it, so it goes from C to D to E to F to G to A to C. And what happens is, when you move this, a sound wave has to fit inside of this particular container, so that just like the string had to fit in there, the sound wave has to fit in. And if you change how deep this goes in, you change the sound. So if I want, I'll try low C, and then D, E, F, G, A, B, C, an octave higher. And of course, what kids like to do is this. Enough physics lesson for the day.